Hello, welcome to the next lecture, 3.03 Factors Affecting the Equilibrium Constant. Now, pressure change will never affect the value of K. However, when you change the pressure in a container, by injecting or removing one of the substances in that system, you can sometimes achieve a shift one way or the other to restore equilibrium. Le Chatelier was one of the first people to describe this. It's something that's not well understood, and it's frequently it's a poorly taught concept in chemistry, so I'm going to take a shot at explaining it to you. When you upset an equilibrium state, the system will adjust to it. The new concentrations will be different than the original ones. However, if the system remains isothermal, it means the temperature doesn't change, then K value will remain the same. So I'll give you an example. Assuming this system stays at the same temperature, the system is A in equilibrium with B and C. And notice it's an exothermic reaction written in with the reactant A on the left and products B and C on the right. So K will equal the concentration of B times concentration of C divided by the concentration of A. So the rate expression for the forward reaction is only going to depend on A. So the rate of the forward will equal K for forward reaction times the concentration of A. And the rate expression for the reverse reaction would be R times, the rate of the reverse reaction would equal K times the concentration of B times concentration of C. Now, if the system is equilibrium, how do those rates compare? They're going to be equal to one another. So again, we're looking at that system. They're equal if the system is at equilibrium. The rate at which A changes into B and C and the rate at which B and C changes into A are the same. So there'll be no change in the macroscopic properties of the system when it's at equilibrium. However, when I inject B into the system, what happens is now with more B particles in the system, the probability of collisions between B and C has increased. The probability that A is going to change into B and C has not changed. But the reverse reaction, because of the presence of more B, is going to increase. It will be at a maximum rate at that instant that B is injected into the system. Because the reverse rate is now greater than the forward rate, B and C will start being converted into A. Now, as more A is produced, then the forward rate will also start to increase until the two rates, the forward rate and the reverse rate, are equal again. Now, when the equilibrium is reestablished, what has happened to the value of K? Nothing. It's unchanged. So let's look at a concentration versus time graph and see what's happening. Concentration on the y-axis, time on the x-axis. We have quantities of A, B, and C. Could be any values here. Just for reference, I've separated them. But what did we say happened? We injected B into the system, so B goes up. Now, when we inject B into the system, again, the reverse rate will now be greater than the forward rate because the probability of collision between B and C has now increased. So that rate will be a maximal value at that instant. And as B and C collide and create more A, the rate will decrease and the quantity of B and C will both go down by the same amount. Meanwhile, the quantity of A, because it's a 1-to-1-to-1 reaction, will go up by the same amount that B and C go down. The new equilibrium is reached whenever the quantities of A, B, and C, the concentrations in the container, are no longer changing. So when we compare the new concentrations to the original concentrations, we can see that A, the new concentration is increased, B, it's decreased, and C, it's also decreased. Keep in mind, never show the quantity of B going down below the original quantity of B that was in the container. So now to compare rates, since the system was at equilibrium before the B was injected, the two rates are equal. However, when I injected B into the container, one rate is going to increase dramatically. And that, of course, is the reverse rate, because with more B in the container, probability of collisions increase. But that rate will start to decline. And as the reverse rate declines, the forward rate will start to increase until a new equilibrium is established. So at this point here, that would equal this point on this graph. The new equilibrium is established. So the forward rate and the reverse rate are now equal. Because there's more B in the container and B was converted into A, the quantity of C decreased, but the quantity of A increased and the quantity of B increased. So there's more total particles in the container, and that means the forward and reverse rates will both increase from the original quantity that was, the original rate that was there. So now let's predict what happens using graphs when we have an equilibrium. Notice between A, B, C, and D, notice the stoichiometric values are slightly different, 2 to 1 to 4 to 3. So we're going to add A in this case. So when we add A, the forward rate should now be favored over the reverse rate. The system will no longer be at equilibrium when we suddenly inject A into the container. The system will shift to offset the addition of the A. So what happens is A is added to the container. The system will shift from left to right to use up the A that's been added. B will get used up as well in the ratio of 1 to 2. C will be produced, as will D, at the ratio of 4 to 3 compared to the amount of B that is consumed. We can show this in the graphs. We can show A rising, and then of course going down. This difference here will correspond to 2x at the new equilibrium. No change is going to happen anymore in A and B. They will be achieved at the same place on these graphs. But notice B has only gone down by half of the amount that A went down, because it's 1 to 2. The amount of C has gone up by 4 compared to the amount that B has gone down. And the amount of D has gone up by 3 compared to the amount that B has gone down. So let's take a look here. If I remove some B, what happens to this system? Well, the Chatelier's principle says if I remove some B, the system will respond to offset the stress. The stress in this case is removing B. The equilibrium will shift from right to left to offset the stress. A new equilibrium will be established. And before that new equilibrium is established, C and D will get used up to produce more A and B. But remember, some B was removed. So we're going to show the quantity of B decreasing. But as the system responds to this stressor, it will increase twice as much as the quantity of D that goes down. So that's our reference, the one that's 1 mole. A will go up 4 times as much as D goes down. D goes down again by that amount, this amount right here, from here to here. And C will go down by 3 times as much as D goes down. So we can just put those values on the curve here just to show it. Sorry about that, it ran away on me. So we've established how Le Chatelier's principle is applied to equilibria that have been stressed. Now, temperature will always change the value of K, because adding heat to a system in a state of equilibrium will always alter one rate differently than the other, depending on which side the heat is on. If we take a look at this particular equilibria, if I add heat to the system, then the equilibrium will shift from right to left to get rid of that heat, thereby decreasing B and C and increasing A. If I cool the system by removing heat, then the system will respond by replacing the heat that's been removed. So A will go down and B and C will go up. Now to find K, we simply take the concentration of B, multiply by the concentration of C, dividing by the concentration of A, or we could use pressures. In this case, I'll just use concentrations. And the rate expression for the forward reaction would be R equals K times concentration of A. And the rate expression for the reverse reaction is R equals K times concentration of B times concentration of C. At the initial equilibrium, the two rates are equal again. Now, heat is added. Which rate is affected more? Well, when we add heat, the equilibrium will shift from right, or the system, I should say, will shift from right to left to use up the heat. A and B will go up, A will go up, B and C will go down as we use up the heat that's been added. So the reverse rate is affected most. Now, which rate is now bigger? Well, the reverse rate increases more than the forward rate, so the system will shift to get rid of the added heat. When equilibrium is reestablished, what has happened to the value of K? Well, the value of K, remember, is equal to quantity of B times quantity of C divided by quantity of A. So if the system shifts and B and C go down and A goes up, the value of K, of course, will decrease because B and C are the numerators and A is the denominator. If B and C go down and A goes up, K, of course, will get smaller. So let's look at a concentration of time graph for this system. So if I, again, change stress the equilibrium by adding heat, then it shifts, goes from right to left. Quantity of A will go up, the quantity of B and C will go down, and the relative quantities, because it's a 1-to-1-to-1 reaction, will all be the same. So this distance, and this distance will all be the same. In terms of rates, the two rates were equal at equilibrium. However, when we stress the system by adding heat, all of a sudden, there was an increase in the reverse rate because it shifted to get rid of the heat. And the forward rate is going to start increasing because as B and C produce more A, if there's more A present, the A will start making more B and C. At a higher temperature, both rates are going to increase. But the reverse rate will start decreasing. The maximal level reached is at that instant that the heat is added. And then a new equilibrium is reached when the forward rate and the reverse rate are equal to each other. So when we compare the rates and the concentrations, the concentration in this case, A will go up, B will go down, C will go down from the original quantities. And the new rate will be greater than the old rate because it's at a higher temperature. Now let's talk about the relationship between K and the balanced chemical equation. So, and also when we reverse it. So if I have an equilibrium for this system, K1 would equal quantity of, or the activity of NH3 squared divided by N squared, or N2 divided by H2 cubed, sorry. And suddenly if I double it, or if I reverse it, I reverse the equilibrium, now we can see that K2 for the reversed equilibrium is simply the inverse of K1. You can see that the denominator on this side is equal to the numerator on the right. Similarly, numerator on the left equal to the numerator on the right. So you can see that K2 is really the inverse of K1. Now, what happens when you multiply an equation by a constant, n? So when we multiply by a constant n, the equilibrium constant becomes k to the power of n. Why? Well, let's investigate this. So again, for the same equilibrium involving nitrogen, hydrogen, and ammonia, K1 is equal to that expression. Now, if we double it, we end up with 2N2 plus 6H2 plus 4 ammonia. Now, when we write our K2 value, we can see that the exponent will be 4 in the numerator, or the exponent again, divided by nitrogen to the power of 2, divided by hydrogen to the power of 6. And when we compare the exponents, we can now see that K2 is really K1 squared, because if we took the original K1 and squared 2, we get 4. If we squared power 1 here, we get 2. If we square 3, we get 6. So now what we're going to do is combine equilibrium constant expressions, the K values. Let's look and see what happens to them. So the K total is really K1 times K2 when we combine two equilibria. So if I have equilibrium 1 and equilibrium 2, the K1 is activity of C over activity of A over activity of B. K2 is activity of E, activity of F divided by the activity of D. When we add these two expressions together, we get A plus B plus D, produces products C and E and F. They have an equilibrium here. The K total will be the activity of C times activity of E times activity of F as numerators over activity of A, activity of B, and activity D. Well, we can see, really, here's K1 and here's K2. So really, all we're doing is multiplying K1 and K2 together to get K total when we combine two equilibria together. So let's talk about using ICE tables to solve problems. ICE, I stands for the initial concentration. C stands for the changes. Also remember, it says watch the coefficients C, because the coefficients in the equilibrium, of course, result in different mathematical results. And E stands for the equilibrium concentrations that are established. Now, remember, as long as the temperature remains constant, the equilibrium constant will also remain constant. So let's look at an example here, an equilibrium involving dinitrogen tetroxide and nitrogen dioxide. You can see 1 mole of N2O4 is in equilibrium with 2 moles of NO2. Now, if we look at the quantities here, notice it says at equilibrium, we have 7.64 grams of N2O4. We have 1.56 grams of NO2. They're present in a 3-liter container. Calculate the value of Kc for this reaction at this temperature. First, we must find the concentrations. So the number of moles is equal to mass divided by the molar mass of N2O4. The number of moles of NO2 is the mass again, 1.56 grams, divided by the molar mass of NO2. That's 3.391 times 10 to the minus 2 moles. And then the concentrations are moles divided by volume. So the moles divided by the volume for N2O4 will be 0.0277 moles per liter. For NO2 will be 0.0113 moles per liter. And now we are ready to fill our ice table. At equilibrium, we were told the quantity of N2O4 and the quantity of NO2. So we can calculate the equilibrium constant for concentrations, Kc. we're going to take the quantity of NO2, and don't forget to square it because there's a 2 in this equilibrium expression. We're going to divide that by the quantity of N2O4, and we get a value of 4.61 times 10 to the minus 3. And it's going to be moles per liter squared over moles per liter, which is moles per liter. Now that doesn't equal the value for Kp. Kp would be calculated using this Kc value and multiplying it by RT times the change in number of moles. And in this case, the right side is 2 moles, the left side is 1 mole, so the change is 1. Again, the arrows show where the change in number of moles came from. So let's consider in another example an equilibrium between sulfur trioxide in equilibrium with sulfur dioxide and oxygen. And we're going to place 0.0200 moles of sulfur trioxide into a container. The container is 1.52 liters. The temperature is 900 K. Now, once equilibrium is established, we find that 0.142 moles of sulfur trioxide is now present. So let's calculate Kp for this equilibrium. So what again I'm going to do is calculate the concentrations, moles per liter. Here's the volume, here's the moles, or SO3. The moles per liter is equal to 0.01316. At equilibrium, the concentration of SO3 was given as 0.0142 moles divided by the same 1.52 liters. There's the value for the concentration of SO3 at equilibrium. So in our ICE table, we know the initial amount of SO3. We know the amount at equilibrium. Well, how did SO3 get from the initial state to the equilibrium state? Well, obviously, when we add SO3, and this system is not at equilibrium, the system will shift from left to right, making SO2 and O2 in a ratio 2:1, using up SO3 in the same ratio that it's producing SO2. So if we subtract the quantity, the initial quantity, and subtract the quantity at equilibrium for SO3, we get a change of 3.8 times 10 to the minus 3 moles per liter. It went down, and notice since 2 moles of SO3 produce 2 moles of SO2, it's going to go up by the same amount that SO3 goes down. Oxygen will go up by half that amount because it's 2:1. So now at equilibrium, we can establish the quantity of SO2 and O2, and we can now figure out Kc. So the equilibrium constant using concentrations will equal quantity of SO2 squared times the quantity of O2 divided by the quantity of SO3 squared. So we arrive at a value of about 3.2 times 10 to the minus 4 moles per liter. And we can calculate Kp from Kc using this mathematical relationship that we have established earlier. So it's going to equal the Kc times R. And recall, we're going to use R as atmosphere liters because it's Kp. We need to use atmospheres per mole, atmosphere liters per mole Kelvin. We're going to use that particular value for R. And the temperature, of course, we were told was 900 Kelvin. So when we multiply that through and cancel our units, the moles cancel, the liters cancel, the kelvins cancel, we're left with our answer in atmospheres. Now, another way to know that the unit will be atmospheres is because if we're using partial pressures, it would be atmosphere times atmosphere squared divided by atmosphere squared. Atmosphere squares would cancel, you'd be left with atmospheres. Now, third example, we have an equilibrium of ammonium hydrogen sulfide in equilibrium with ammonia and hydrogen sulfide. We're told the Kp value at 25 degrees Celsius, and we're asked to calculate the total gas pressure of the system at equilibrium if a sample of ammonium hydrogen sulfide is introduced into an evacuated flask and allowed to reach equilibrium. So if we set up our ice table, we know that some ammonium hydrogen sulfide was introduced in the container. We weren't told how much. But we do know in order for this system to achieve equilibrium, we're going to use up ammonium hydrogen sulfide. We're going to create ammonia gas and hydrogen sulfide gas. But the other thing is, this is a heterogeneous equilibrium where the solid is making two gases. So we know the left side goes down, the right side goes up. These will go up by the same amounts as this goes down. And now Kp is going to equal, we're told it was equal to 1.1 times 10 to the power 3 kilopascals squared. That's going to equal the pressure of ammonia times the pressure of H2S, which of course equals x squared. Well, we're given the value of Kp. We know it's equal to x squared. Well, we can solve for x. How do we do it? We take the square root of 1.10 times 10 to the power 3 kilopascals squared. We get a value of 33.2 kilopascals for x. But notice we're asked to calculate the total gas pressure in the system. There's two gases in here, and both are x. So to get the total pressure, we are going to take x, multiply it by 2. So 2x is equal to 2 times 33.2, which is 66.4 kilopascals, the total pressure. Now another example, we have the equilibrium of N2O4, dinitrogen tetroxide, equilibrium with nitrogen dioxide. We're given the Kc value at 25 degrees, and we're told that we're injecting 0.0240 moles of the dinitrogen tetroxide into a 0.372 liter flask at 25 degrees Celsius. Calculate the concentration once equilibrium has been established. So we're going to calculate the concentrations because we're given moles. It's moles per liter. Concentration of N2O4 is given to us. Now we know that the system will not be at equilibrium at that point. We know that some of the N2O4 is going to get used up to make NO2. The amount of NO2 consumed and the amount of NO2 produced will not be 1-to-1. It'll be 2-to-1. So N2O4 is going to go down as it's used up to make the NO2. NO2 will go up by twice as much as N2O4 goes down. So that at equilibrium, we know the original amount of N2O4, we know it goes down by x. And we know the quantity of NO2 only comes from the breakdown of the N2O4. So it will be 2x. The equilibrium constant Kc is going to equal the quantity of NO2 squared divided by the quantity of N2O4. We know the constant, which was given in the question at 25 degrees Celsius. The temperature hasn't changed throughout. So we can now solve for x. So we're going to take the quantity of NO2 and square it and divide it by the quantity of N2O4. In this case, in terms of x, it's 2x quantity squared. A lot of people forget to square the 2 here. Please don't do that. Divided by 0.0645 minus x. And now to solve, we're going to square 2x. We get 4x squared. And then we're going to multiply 4.61 times 10 to the minus 3 times minus x. And we're also going to multiply by 0.0645. And then we're going to move those terms all to the left to establish a quadratic equation. Once a quadratic equation is solved, we now know A, we know B, we know C, and we know x equals minus B plus or minus the square root of B squared minus 4AC. So using that quadratic equation, we can solve for x. We get a value of 8.06 times 10 to the minus 3 moles per liter. Again, the unit is moles per liter times moles per liter divided by mole per liter. It leaves mole per liter. Now, that is the value of x, but we were asked to find the concentrations. So we can find the concentration of N2O4 now that we know X. We have to subtract the value of X from the original amount of N2O4, and that's going to leave us with 5.61 times 10 to the minus 2 moles per liter for N2O4 at equilibrium. Similarly, the amount of NO2 at equilibrium will be 2 times X. So 2 times 8.06 times 10 to the minus 3 is 1.62 times 10 to the minus 2. We've solved our problem. The last example here, we have solid silver is added to a solution with initial concentrations of silver and iron. There's two different ions of iron, and there's solid silver. Doesn't make any mention of an equilibrium. It does say it will reach an equilibrium. So what we're going to do first is find the Q value to see if the system has to shift from right to left or left to right. We can only determine that if we know the value of Q. We can find the value of Q using all the freely mobile particles, the aqueous particles. Remember, the activity of silver will be 1 because it's a solid. It won't be included in Q. So we're going to take the quantity of ferric ion divided by the quantity of ferrous ion and the quantity of silver ion. We were given those quantities. So again, we take 0.3, the quantity of ferric ion, divided by the quantity of ferrous ion and the quantity of silver. We arrive at a value of 15 molar to the power minus 1, because these two cancel. We're left with 1 molar quantity on the bottom. But we were given Kc was 2.98 liters per mole. Q is bigger. So what do we have to do to reduce the value of Q so it gets to an equilibrium? Well, we have to decrease the products. We have to shift the equilibrium, the system, from right to left. These quantities are not at equilibrium. It will reach equilibrium, but the system has to shift from right to left in order to establish the equilibrium. So we knew the quantities of those ions that were present. And now we know it has to shift from right to left because we compared Q to Kc. We know that the ferric ion has to go down by X. Silver is going to go down by X. The ferrous ion is going to go up by X, and the silver is going to go up by X. So that at equilibrium, we now have established the various quantities related to X. So can we solve for X? Well, we do know Kc, and we do know Kc is 2.98 molar to the minus 1. Then it's equal to ferric ion divided by ferrous ion divided by silver. And we substitute in the values for ferric ion in the numerator, ferrous ion and silver in the denominator. We can now cross multiply. We can expand this. So we get 0.2 times 0.1, it's 0.02, 0.2 times plus X times 0.1, and then X times X. We're going to multiply everything in this term by 2.98, and that equals 0.3 minus X. So we can bring everything to one side to make it equal to 0 by subtracting 0.3 from each side and adding X to each side. So when we add 1X to 0.894, we get 1.894X. Similarly, we're going to subtract 0.3 from this quantity, and we get 0.2404. Okay, and I believe, okay, we can solve the quadratic equation again using ax squared minus bx plus c. I think this value was supposed to be a negative here, so keep that in mind. but I'm confident that the value of x in the quadratic equation was solved using minus here. So the quantity of silver, we know, is equal to 0.2 plus x. So we're going to take 0.2 and add it to x, which was 0.11. We know the quantity of ferrous ion was 0.1 plus x, giving us a value of 0.21 moles per liter. And the quantity of ferric ion is going to be 0.3 minus x, where x was 0.11 again. And we now have established the equilibrium concentrations of silver, ferrous, and ferric ion. Now we can check to see if this is correct. We could do that by, again, finding Q. Now, if it's correct, Q will equal K. So Q is the ferric ion divided by the ferrous ion divided by the silver ion. We take the 0.19 molar divided by 0.21 molar divided by 0.31 molar, and we get an answer of 2.9. We were given the, now, if x were given to 3 significant digits, the answer would be 2.98. So looks like our results are good. These are only 2 significant digits. If we made them each 3 significant digits, chances are we would get 2.98. Here's the homework, and I thank you for tuning in. Good night.